Good morning, guys. This should be a relatively short video because this is going to be very calculator heavy. I may not actually even go through all the examples because if you look at the notes, you can see that every example except for the last one is about analyzing a graph. Now, we could go through all the algebra steps again, but I told you this class is more realistic than anything else. So we've talked about the understanding aspect of how to do these problems, how to use the algebra to find certain key critical values for each one of these graphs, and then to use that information to generate the graph. So what we're going to do today really is just go through and graph these on the calculator and then use the calculator to find the critical values that we are looking for. So example 1, it just says analyze the graph of the rational function f of x equals x minus 1 over x squared minus 4. So as we've done in the past, we're going to use Desmos today. So we're just going to type in the equation x minus 1 over x squared minus 4, and that is x sub 62 x squared minus 4. There we go. So there's our graph of the given function, and you can see, looking at the the graph there on the right, we have two vertical asymptotes at -2 and +2. If we wanted to find those algebraically, we would simply just graph or set the denominator not equal to 0, solve for x, and we would also come up with the same two values, +2 and -2. We have a y-intercept. You can actually hover over this of 0.25, and we have an x-intercept of 1, 0. We also note that as the graph moves out towards positive infinity, it gets closer to 0. As the graph moves out towards negative infinity, it also gets closer to 0. So that's really all the analysis is. You just graph the equation, you find some critical values, you note the asymptotes if they exist, and then you move on. Not a lot to this. Example 2, it's x squared minus 1 over x. So we'll go back to Desmos, and we're going to graph this one. Let's see, it was x squared minus 1 over x, and there's our graph. And we see that this one has two x-intercepts at -1, 0 and +1, 0. It also has a oblique asymptote. The degree of the numerator is one more than the degree of the denominator, so we would go through the process of long division. And when we do the polynomial long division in this case, we find that the oblique asymptote is y equals x. And I'm just going to go ahead and graph that in right here. You can see that oblique asymptote now, the way it splits the graph. The graph in both cases approaches that asymptote but never actually crosses it. With our third example, we are looking at x to the 4th plus 1 over x squared. So let's go back to the graph. We have x to the 4th plus 1 over x squared. And here's our graph. We have no x-intercepts. We do have these two minimum values. We have one at -1, 2, and we have another minimum value at 1, 2. 0, x equals 0, is a vertical asymptote of this graph, and that's the analysis. I mean, really, we can see as x approaches positive infinity, or as x gets larger moving to the right, we can zoom out on this if I can figure it out myself. There we go. Zooming the wrong thing. Sorry, guys. Get this back to 100%. Here we go. We can zoom out. As x gets bigger, y obviously gets bigger, but it's getting bigger very, very rapidly. So when we get way out to, say, 1,000,000, it's going to be exceptionally large based on the values that we are looking at with this particular problem. Let's see. Get back in. Okay. example 4, again, we would just graph that and analyze it. Same thing with example 5. Like I said, I don't want to, we can get through this one really quick because it is just strictly calculator heavy, with the exception of example 6. So this is where we need to do a little bit more work, and then we can go back and use the calculator. So I'm going to pause this for a minute so I can detach the screen from my computer so that I have something to write on. So give me just a moment. Okay, so what we're looking at here, it says the Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder with a capacity of 500 cubic centimeters. And we want to, let's see, top and bottom of the can are made of a special aluminum alloy that costs 5 cents per square centimeter. The sides are made of a material that costs 2 cents per square centimeter. Part A, express the cost of the material for the can as a function of the radius of the can. So we're going to put to use my terrible art skills. So here's my can. And we know that we're trying to figure out the cost for the top and the cost of the bottom of the can have one particular value, and then the cost for the side of the can has another value. So we have to go back to geometry a little bit. Remember the top and the bottom of the can, we have two of them, and the area for a circle is pi r squared. So the area is pi r squared. That's for the top. We double it and we will have the area for the top and the bottom. So that's going to be 2 pi r squared. Then the area of the sides, if we unroll this, it would look like just a rectangular piece of paper. It would just be a rectangle if we just simply unroll the sides. And the length of one side is going to be the circumference of the top or the bottom of the can. And remember, the circumference is equal to pi times diameter, or 2 pi r. And the question wants us to find the cost of the material as a function of the radius. So we will apply that using this information that we're given. And since we have the circumference, to find the area that we've expressed there in green to be the area of the rectangle, that area is the length of the rectangle times the height of the rectangle. And the height is one of the things that we don't know, but we know that the length is going to be expressed by the 2 pi r. So the area of the side is 2 pi r times h. So when we're trying to express the cost of the material as a function of the radius, we have to start putting some things together. The first thing we know is we're going to call this equation 1 and equation 2. Equation 1 gives us the area of the top and the bottom of the can. And we know that the cost of that material is 5 cents per square centimeter. So we're going to have 2 pi r squared times 0.05. And then we would add the cost of the sides. And the side is 2 pi RH times 0.02. That's the cost of the material for the sides of the can. And then now we have this one extra variable floating around in there, the h, that we need to figure out a way to get rid of. And the way we'll do that is by utilizing the fact that we're given the volume of this can. Remember, volume of a cylinder is pi r squared times h. Well, in this particular problem, we know the volume to be 500 cubic centimeters, and that's equal to pi r squared times h. And if we take the equation 500 equals pi r squared times h and solve that for h, we'll have a replacement value that we can use in the formula there in pink to replace our value for h with. and then we'll have an entire cost function in terms of r. So all we have to do is divide both sides of this equation by pi r squared, and we'll end up with h is equal to 500 over pi r squared. And then now we can go back to our cost function and substitute that in. And we're going to get this cost function as a, in terms of the radius, is going to be, let's see, 2 times 0.05 will give us 0.10 pi r squared, plus, and then we have this 2 pi r, and we're replacing h with 500 over pi r squared times 0.02. So we need to clean this right side up, what's to the right of the plus sign, a little bit more. And when we do that, we will notice that the pi's here are going to cancel. Our radius, we'll lose one of those, and we're going to end up with 1000 times 0.02, which will give us 20 over r. So now we have this simplified form of our equation is 0.10 pi r squared plus 20 over r. And so now we have a cost function in terms of the radius that we can use to finish out and answer the remaining questions on this problem. And the easiest way to, let's see, let me scroll back up here. So use your calculator to graph the cost function. So what we need to do now is we're going to take this equation that we've generated, and we're going to just type it in onto Desmos, where we have to replace r with x for the purposes of typing it in the calculator. But I can, if I can get this to open. Well, now I'm not having so much luck. There we go. Okay, so let's see if I can remember it off the top of my head. I probably won't. It's 0.1 pi x squared. Try that again. 0.1 pi x squared plus 20 over x. Okay, so I did remember it, I think. Let's double check. Okay, so that is it. And we use that graph to find the value of x that will generate the least cost, and then we want to determine what is the least cost. So let's go back to our graph. Boy, I'm having a difficult time with the technology today. And here we need to zoom out so that we can see what's going on with this graph. And we have this vertex that you can see right here, if I can zoom in on that some. And this is where our least cost, our value for x, or in this case r, is going to give us the least cost. So 3.169 will be the radius that will generate the least cost, and $9.47 will be the least cost that can be obtained for a can of this particular size. So that's all you'd have to be able to figure out, is you just find that minimum value on the vertex, keeping in mind that we substituted x for r, and we come up with a radius of 3.169 centimeters. Will generate a least cost of $9.47. And that's the end of these notes. The homework should be or the suggested problems, I apologize, should be pretty straightforward. We have, I believe, 1 or 2 more sets of notes, and then there's going to be a test. The test will be available for a couple of days for you to work on. And we'll just go from there. So remember, if you have questions, please just shoot me a message on Remind. Let me know. Email me, whatever you have to do to get a hold of me, and we'll address those questions. I hope everybody's doing well, and I'll be talking to you soon.